Welcome, everyone. We're pleased today to have Professor Beth Stadler here from University of Minnesota. She's a professor and associate head of electrical and computer engineering, and also member of chemical engineering and material science and mechanical engineering. There's a lot of faculty meetings to go to. She's a distinguished professor and holds the CSE distinguished chair. So she's been working in magnetic fields for a long time and held many positions in the Magnetic Society. And we've enjoyed collaborating with her. So she's the world expert at integrated optical isolators. So without further ado, Beth Stadler.
Well, I can think of like 3 or 4 other people who would join me in loving optical isolators and doing a lot of work in that field. So I'm happy to be counted among that crowd. Right, so I have here just Magneto-Optical Garnets, and I realized in going through the labs here that I probably should have spent a little more time on the materials, but I do have materials information, a little less on devices because this crowd's probably very familiar with the devices that I'm about to share. John, is that right? You think that most people here have the interferometers and the ring resonators are something they're familiar with?
Yes.
Okay. Then I might hop through those a little bit quicker. And then I just have here, because we had a MRS bulletin that was describing isolators, and so we had this graphic made up of the idea that all of the arrows going forward are transmitting light, but the one where there's reflection, so there's light coming backward, it can't go past your isolator. So being in electrical engineering right now, I think of these isolators as optical diodes, but it is funny, depending what crowd you're talking to, people may or may not know what you mean by that. So what I mean is, in a reciprocal material, the light is going to go, let's say, from your left to your right. And if anything goes backward, the material doesn't look any different to it. So one example is, if you can see my arm, if light is rotating this way when it's coming towards you, it would rotate back when it's coming towards me. And that means wherever it started, if it propagates forward and comes back, it's still backward in the same position. Non-reciprocal means something's happening on the way forward that is different on the way back. So what you end up on the way back is different. And in the case of diodes, you just want to make sure that something happens in that non-reciprocal device that the light can't propagate backwards, or maybe you send it off to a different channel. So the 3 ways that you can maintain reciprocity, which most materials do, is you would want to have symmetric permeability and permittivity sensor, like so. There's no off-diagonal component to this dielectric matrix or the permeability matrix. And this is most materials, really, so not so hard. You might have different, like bi-refringence would be where XX and YY are different, but still there's nothing on the off-diagonal. Another way to keep reciprocal is that the material is optically linear, meaning all of its properties are the same no matter how much power of light you're putting through that material. Or we also kind of assume that most materials have optical properties that are time invariant. So there's no reason why a material would change its properties over time. So we're going to focus on the first one, because the second, if you want to change the reciprocity and make it non-reciprocal, you have to break one of these rules. The second rule is really best broken if there's a lot of light power, because nonlinearity is related to the power of the light. And a lot of the things we're looking at aren't for high power beams. And this second one is, in some cases, people have made like p junctions where they change the propagation constant and it really changes in one direction. So then light couples with that propagation constant, but not in the opposite way. But to do that change, they're actually putting in power. So it means it's an active device, not a passive device. So we are interested in this first rule here, because if we can give ourselves some off-diagonal components to the dielectric matrix, it means that we don't have to supply power, that the material itself is non-reciprocal. And so we'll end up breaking the reciprocity rules. I realize actually for people online, I don't have my laser pointer. So this is the dielectric matrix, and you can measure Faraday rotation pretty easily in a lot of different materials. And this is how you would just back out of it, that what we might call gyrotropy, by knowing the Faraday rotation. So I think a lot of people in this room know commercial isolators. I'll just say briefly that commercial isolators, if you buy one for your lab bench or one that's fiber coupled, you'll have a garnet that's active. Either it's on a GGG substrate, so the film that's on that substrate is the yellow part, or sometimes you just grow a thick enough garnet that you can take the substrate off. And then there's a polarizer and a ring magnet. The idea being forward propagation goes through that polarizer, and any light that passes through the garnet is rotated. If some light happens to go backward through the garnet, it continues to rotate in what looks like the same direction from the input point of view. From the outpoint point of view, it looks like it's rotating in the opposite direction because it's opposite to the magnetic field. Either way you think about it, it ends up in 90 degrees, the polarizer blocks it. So that's just like buying something off the shelf. That's probably what it has in it. So here's the magneto-optic garnet. One of the things my group has done for quite a while, this is actually from 2005, and I really wish I had looked at a couple of these images, but you can look up this paper, maybe you've already seen it. But the thing is, the garnets have 3 different lattice sites for the cation. So the dodecahedral site, basically, if you're familiar with a face-centered cubic structure, if the face-centered cubic structure is all oxygen, you fit in between those oxygen cations, so they're plus, they hold the minuses together. And if there's 8 oxygen around any particular cation, it means it's a pretty big site. So that dodecahedral site, that's what it looks like. The octahedral site, like it sounds like it looks like an octagon where there's 4 atoms on the around and 1 on top, 1 on bottom. That's a smaller site, but kind of medium sized. The tetrahedral site's very small. So there's 3 on bottom and 1 on top, and there's oxygen, and there's a cation in the middle. That cation has to be smaller to be able to hold that tetrahedron together. So basically you have small, medium, large cations. Actually, half the periodic table can fit into garnet structure. But you have to balance the ratio of the 3 different sites. So if you have some rare earth element and iron, there's a fair number of rare earth iron garnets that you can form. If you find garnet like as a gemstone in nature, it's probably got more like calcium and aluminum and iron or something in it, but not the rare earth ion. So we have kind of made a habit of mixing and matching what we put in the garnet to get different properties out of it. And to get Faraday rotation out of it, there's one more factor that comes into it. There's a coefficient in front of every element. And sometimes there's even charge transfer between elements, which gives you any resonant peak can give you some Faraday rotation. All right, so one of the things we realized early on is the way you make the garnet matters a lot. So for example, if you just put down yttrium and iron and oxygen, and you want to get Y3Fe5O12 because you want to form garnet, well, that's this spot. If that would just be this this binary phase diagram, we'll call it. If I could look at the edge of that triangle, what I would see is that if I have all yttrium and oxygen, I'd get this Bixbyite structure. If I have half and half yttrium to iron, but still 1 to 1 to 3 oxygen, I'm going to end up with this perovskite-like structure. And then there's garnet if I get 3 to 5 to 12. And finally, if I'm fully at iron and just oxygen, I'll get this hematite phase. But it turns out I found this phase diagram when I could not explain why, depending on how we anneal the garnet, we would get all these different phases. So way back in 2005, it turns out I might get this perovskite, Bixbyite, and this orthorhombic phase, but I wouldn't even see garnet. Other films where I put down 3 to 5 to 12, so I was sure I had what should be the garnet structure, I would actually get, again, this perovskite, this orthorhombic, and some iron oxide. I wouldn't even have one of the phases be garnet. And once in a while, we get garnet. And what this phase diagram told me is these things are called compatibility triangles. When you get to a certain temperature, there are certain phases that are stable together. And this over here, this peak is telling me that basically if I deplete my film of oxygen, I'm going to end up in one of these 2 compatibility triangles. So I make this composition, or maybe I'm a little off composition and I end up in A, or I'm a little off composition, I end up in B, but I don't get garnet. So we started annealing in oxygen and got garnet like every time after that. So it turns out the way you make it really matters. The other thing that matters is you can vary this thing called a compensation temperature. So this is looking at those sublattices. The blue is the dodecahedral. So if your rare earth is magnetic, yttrium, for example, is not magnetic, lanthanum's not. But if you have terbium or gadolinium or most of the others have some magnetization to them. their moment versus temperature looks like this. And if you have iron, at most temperatures, iron's either all up or all down. And it turns out your ion sublattices are antiferromagnetically coupled to each other. There's this super exchange that happens with the oxygen between them. So if your tetrahedral sites are magnetized down, your octahedral sites will be magnetized up. That's it, unless you're close to the Curie temperature. That's how they align. But this dodecahedral site aligns with the octahedral magnetization, but you can see it actually gets pretty low here, then goes to 0. So if there's 2 octahedral iron for every 3 tetrahedral iron, which is what that composition gives you, it means when your dodecahedral site hits 1, you've got 1 plus 2 equals 3. So your net moment is now 0. And then after that, your net moment, it turns out, would become negative, but you don't really ever measure a negative magnetic moment. So when you're measuring it, what you'll end up measuring is this bounce right at the compensation temperature. And the interesting thing is this fact over here, below the compensation temperature, if your moment is facing in one direction, your Faraday rotation is positive along that same direction. But when you get above that compensation temperature, even though your moment realigns and it looks like it's in the same direction, you'll have the opposite sign to your Faraday rotation. So what a lot of people did, like in the 1990s, is they would even just take garnet grown on garnet, and they would heat up one area or they'd cause a little diffusion to try to shift it. So they'd say, well, if I'm sitting at 300, if I make an iron gallium garnet, I can shift the compensation temperature from this side of 300 to this side of 300, and every other segment of my garnet will be positive and negative and positive and negative. And they did that just by barely shifting how much iron they basically had, right? So if you add gallium, you're wiping out the tetrahedral iron, and it means your balance of tetrahedral and octahedral shift, so your compensation temperature can go on either side of room temperature. So it's just another way to kind of play with the chemistry to get the behavior you want. So I put down a couple of review articles that have been put together over the last couple of years in case somebody isn't familiar with garnets. This one is Kelvin. Yeah. I should put that down there. The fact, I guess, that it ends at 0, I kind of assume, but you're absolutely right. It could be it goes past that point and I just didn't put it on there, right? I might just keep getting bigger, yeah. All right, this is the part I'm pretty sure your group knows. There's why does it matter for co-packaged optics? You know, there's these data centers. There's a lot of optical fibers that are in your communications. I actually don't want to spend a lot of time on the slide because I realize in this group, probably a lot of you could come up and give this talk. But the main thing is the closer we get the electrons and photons together, the more energy efficient our system's going to be. And I've seen several co-packaged optics being worked on today as we wandered through the labs. But of course, as this group knows better than probably anyone in the world, if we could actually get all of those electronics and photonics on the same chip, that would really improve performance. And there's lasers that are being developed to be on chip. As you know, there's the DFB lasers that I saw measured here. There's the new quantum dot lasers that have been developed here. And there's modulators, you know, a lot of electro-optic modulators that work pretty well on chip, detectors, waveguides, and so on. But the one thing that's really missing still is isolators. So the problem is that these lasers are extremely sensitive to reflections, except I guess the quantum dot lasers, they're a lot less sensitive. And so you can do things like just divert reflections away. There's a lot of strategies to just see that the reflection doesn't hit your laser. But in the end, if you could protect your laser from back reflections, your performance would be better. And this is actually one of the devices that I learned about when Professor Bowers came to speak in Minnesota, actually to collect our Distinguished Alumni Award. Luxtera was just getting started then. And he said, you know, they have this, the laser. Well, let me actually show the cross section, which I found on Luxtera's site. Luxtera is recently bought by Cisco. And there's a laser. It focuses the light in a ball lens, so it can go through a garnet. So this is thing that you can buy and pick and place with robotics that will do your isolation for you. This is just a piece of garnet. I'll talk a little bit more about that in a minute. The light goes through that, bounces down, all of your silicon photonics are down here. So if you could put the laser down here, right now there's not a very good way of putting garnet right here to make sure you have an isolator with all the rest of your photonics. This garnet, it turns out, is it's what they call latched garnet. And that was developed by Vince Fratello at, it was AT&T, then Lucent, then Gear, and then he started Integrated Photonics. That company is in New Jersey, and they were bought out, I think 2 years ago by II-VI. Latched garnet is made in such a way that the growth anisotropy and the strain anisotropy, there's several. So let me just say that most magnetic materials, if they're in the shape of something like this, the moment wants to be in plane. It's just called shape anisotropy. And if you have a magnetic material, like the other thing my group works on is magnetic nanowires, the moment really wants to be along the shape of the structure. One way to think about it, I know it's kind of elementary, but I think just picture the vectors. There's a lot of, not so many would have to come out the tips, but if I made it so the moment was easy around, there'd just be a lot of vectors coming out of here, and that just equals energy. And there's other ways to do an energy balance more mathematically, but that's what happens. So if I have a film, and these things that are placed here, although this looks like a square, it's probably a 300 micron film. They've probably removed the substrate so that it is just a 300 micron film that's been grown on GGG. And then there's a little piece of it, but it has a little bit more of a shape like this. So how do I get the moment to pull out a plane? Turns out, if you use an external magnetic field, what you need is 2 pi times, for a film, it would be 4 pi times the saturation moment, because the moment wants to lie in here, and it would take 4 pi times that moment to come out. That's how much field you need. If you had a shape like this, you'd only need 2 pi ms to get the moment to come out of the pen. So to get away from that, what they've done is basically created a strain on the atomic level. And that gives them a moment, because the crystal structure has a bit of a tendency to point out of plane. They can get the moment to lie out of plane. So it's all about what composition and how it's grown. And they have on the instructions for these, if it gets demagnetized, then you can put it in a magnetic field of about 4 kilooersted and it'll remagnetize. Even if it goes in plane, because this is still one direction, it doesn't mind pointing. But if you get it relined up the way you want it, it'll hold there. Unless you go to a high temperature or you expose it to a really high field. And then it's interesting that they tell you, like, how do you reset your garnet after you've made it? All right, I really did want to belabor that point of shape, that shape matters. You need a magnetic field or some trick to get a moment to point out of plane of a film. We'll come to that later. All right, so ideally, as you already know, I'm sure, if a lot of the lasers are TE. I'm not sure if there's a TM laser out there yet, not that I know. So you want TE to pass through your isolator, and you want TE to propagate to your photonic integrated circuit. TE, if there's a reflection, it's probably going to be TE. So you want your isolator to turn it into either TM or block it. That would be an ideal isolator. So how do we get garnet onto something like a silicon photonic chip? Yes.
Go back to what they're doing.
Yeah.
There. How do they? There's no polarizers what they're doing.
Right. So from what I understand, when it becomes TM, the laser is transparent to the TM mode. So it just goes through. They don't have to block it. And I might have that wrong, but we've talked to a couple people who think that's the case. But sometimes it's hard to get the actual, but I'm pretty sure that's. All right. So hybrid, if you have grow your own or buy garnet, like a doped gig, which are the best Faraday rotators on GGG, you can, that's gadolinium and gallium garnet, which is just a good substrate. As I said, you can get rid of that substrate or just thin it if you don't like it, or if it doesn't matter, because you're going to take your silicon photonic and paste the garnet down on top of it. That's one way to make sure that there's garnet next to your silicon waveguide. You do want to have this doping for high Faraday rotation, and single crystals get like minus 4,500, minus 4,000 degrees per centimeter. Sputtering is very convenient because it is large scale. So you can sputter, regularly people do sputter very large wafers. So we think that if you put garnet down this way, you can also have, you can make a lot of devices all at the same time on a 4-inch, 8-inch, 6-inch, whatever, large wafer. It does require an anneal. That's kind of a showstopper for some devices. So it means if you're going to put on top of silicon, you want to anneal it before you put down the laser or anything else. Kind of like the nitrides. I guess if you have to anneal that, anneal your garnet while you're at it, and maybe it won't matter. But you do need a seed layer for the common cerium-doped YIG. And that was actually an interesting study where Carolyn Ross's group at MIT took the method we had figured out to put garnet onto silicon and said, oh, you know what? If we do that with undoped and then anneal it like Beth did in Minnesota, then we'll put doped garnet on top of that and anneal it again. So I'll discuss that in a minute, but they used pulse laser deposition instead of sputtering. Pulse laser deposition is almost like LPE in that it makes really nice quality films, but it's not very high area. So I think it's a great way to study new devices, but it could be difficult if you want to do like a 6-inch wafer. And the interactions they report between the substrate and the film are pretty low, except they do have a few reports recently where they've used our terbium iron garnet and gotten actually some pretty good Faraday rotation out of doped terbium iron garnet. Terbium iron garnet is one that my group kind of figured out by looking at those balancing the cation ratios. How can we make sure that we get the garnet to form without forming those other phases? And terbium iron garnet doesn't need to be seeded on silicon to still give you a good crystal structure. And the very last part of the talk, I thought maybe Karthik could share with you a new discovery that he just made where we can exfoliate it without using any kind of intermediate layer. Yeah. Oh, if you want to grow it yourself, what Mizumoto, at least in a lot of his papers, they sputter on garnet substrates. Oh, I call it hybrid because you're sputtering on a substrate that's not your silicon waveguide. So if you want monolithic integration on your silicon waveguide, then you'd want to either sputter or use pulse deposition to put the yttrium iron oxide on your silicon wafer monolithically. Yes, that's what I mean. Well, so the way they actually make them at 2.6, and there's another company in Japan as well, they use liquid phase epitaxy. New garnets you can do by any 3 of these methods. Yeah, no, I'm not very clear with this slide. Actually, I just shuffled the way that I put it on here, and I realized it doesn't flow very well. A lot of people used garnet on garnet because that's all they had at first. We developed a sputtering to put cerium-doped YIG, which is what does the highest Faraday rotation. And pulse laser deposition can also put down the most popular garnet on silicon. So these 2 are monolithic. These are new garnets that can be monolithically integrated with silicon that don't need seed layers. So it can either be, you could grow this material right on silicon without a seed layer, and you'll have excellent Faraday rotation. Right. It grows as a garnet without a seed layer. So if I could just repeat what he said, if you are using one of these 2 methods to put down the highest Faraday rotation garnet, picture that you have a wafer and you have it patterned with photoresist. You sputter yttrium iron garnet with no doping on it. You don't have much Faraday rotation, minus 200 degrees per centimeter at 1550, minus 200. All right, then you have to rinse the resist because you're going to anneal it at 900. Then you have to repattern your resist, put down your doped cerium or bismuth yttrium iron garnet. Now you get maybe even as much as minus 4,500, maybe minus 36, maybe minus 2,000, but still at least 10 orders of magnitude better than undoped YIG. So if you could just put down YIG and anneal it and be done, well, you'd pattern it, put down the YIG, rinse off your photoresist, anneal it, you'd be done, but you only get 200 degrees per centimeter. So you have to repattern all of it, put down the doped garnet, strip that resist off, anneal it again. It's just a lot of extra processing. So we found this terbium iron garnet that forms garnet without a seed layer. You just put down your resist, put down your terbium iron garnet, strip the resist so you can heat it, and then you get garnet. And you get a pretty good Faraday rotation. We pretty regularly get like minus 3,200 degrees per centimeter out of cerium-doped terbium iron garnet. And the latest report that Carolyn's group had was they actually got like twice that in Faraday rotation. So it's, I think the terbium iron garnet as a host instead of yttrium iron garnet is proving to be a good host. And yeah, you do need the anneal. However, that's a nice question because I was about to say the other thing that I'm excited about recently is when we were studying the terbium iron garnet, there were certain anneals that Karthik did, and we realized there's this like, it's not like blistering. Like sometimes we were discussing how films can crack, especially if you have a large area. If all of this was just garnet and you anneal it, it cracks more readily than if you pattern little areas, strip the resist, and then anneal it. Those little areas don't crack as much. But there's a certain anneal that we had that it wasn't cracking, but it would, I'd almost say blister off, but blistering you picture being like frosted glass in the way it looks. This was like sheets of it came off. So we'll show you that later because we think that might be the next thing. You could lift off those sheets and transfer print it. It does make it hybrid again, but there's no substrate. You make the film that you want, peel it off and put it where you want it. And there's a group that's doing something called remote epitaxy now. I don't know if you've read about that. They put one sheet of graphene on a 3,5 substrate, put down more 3,5, and then they can lift off the 3,5 film. Perfectly crystalline. If they get multiple monolayers, it'll be polycrystalline. So we can talk about that maybe when we get to that point, but the people that worked on that have now done garnet and a couple other materials as well. Get a single crystal substrate, put a sheet of graphene. A film can grow on top of that epitaxially, basically, and be peeled off, but then you've got the graphene there. So we were kind of thinking, well, this is really neat. We can exfoliate without that graphene. So if you want to look that up, they're calling it remote epitaxy. All right, so as I said, I won't go as much into the devices because I think a lot of your group is familiar with these devices. And I just put a bunch of different devices in this review paper a while ago, so I thought I would highlight that. Here, just an interferometer. I saw several today, so I hope there's not some in the audience who's like, well, I'm not working on that just because you saw some today. I think probably a lot of you are. You have an input here, you break it into two branches. The key is if you have a reciprocal phase shift of 90 and a non-reciprocal of minus 90, the output looks like it doesn't have any phase shift compared to the other branch. So it constructively couples forward. Destructively backward, because this is non-reciprocal, it's now positive, it adds to the reciprocal, and you get a destructive or this kind of like radiated out the wrong way, light on the way back. And there's ways you can do this, what we call push-pull, where you make the two branches, one has a phase shift forward and the other has a phase shift back. So you can make your device shorter if you have this structure to it. The question is, what? Oh, I don't know if I heard a question.
Go back.
Oh, yeah.
Back one more question. So you have 90 degrees here, but when you have two of them, why do you still need 90 degrees on?
Yes. In this case, it's not quite 90 degrees because it's the way these things stack up. So you actually have like, it ends up being the phase difference. So you get like 45. I always have to think about how this works out. Let's see, going forward, I think you add up to 2 pi. So this ends up being pi and half pi and half pi. Right. Actually, I should change the graphic here, but essentially you don't need them both to be 90 anymore. So if this is 45, that's it. Okay, if this is 45 and this is 45, then they add up to pi, and this one is 45, right? So then they'd add up to the difference between the two branches would not be anything. Coming backward, this would still be 45, and you would get 45 instead of plus, it would be minus, so minus 45. I'm not sure that quite works out again. In the end, what you need is the difference between these branches going forward to be the same and the difference coming backward to be off by pi. Yeah.
Why does it only work for TM?
These work for TM because they're 220 So I think it's just the geometry of the light, because I do have, for example, the one that you've worked on where you edge coat. So if your light is propagating forward and you have a transverse magnetic field, then you get a phase delay in the TM mode. If you have your sidewall coated and an upward pointing magnetic moment, then you'll have a phase shift in TE. But in this geometry, only TM phase shifts. Yeah. So if they only work for TM, and that means you also need to have the 220 nanometer thickness usually to get the best, or you need a longer device to get the best interaction between the TM mode and the garnet. You have to have a pretty thin film. You need a full reciprocal polarization converter on both ends, because you go from TE to TM before your interferometer, and then another full reciprocal, really it's mode converter to get TE again back into your system, and then the same thing coming back. So the first one of these that I ever saw made was by this group. Actually, I worked with Samir Ghosh and EMEC for my sabbatical, and he actually came up with a very clever idea. We were discussing how to sputter garnet, but he had a 3-hour train ride from Ghent to Leuven. So for him to come to the EMEC clean rooms and put down monolithic garnet was really difficult, and difficult to find a place to stay or try to make that commute. So he actually took the garnet on garnet that you can buy and put super glue on it and stuck it to the waveguide. It worked great. So this paper and others that he made were just by adhering garnet on garnet to silicon photonics. So what you'll notice here is that the light is in the top branch going from your left to right whenever there's a magneto-optic coating on it. But in the bottom branch, it's going from right to left, right? Because it snakes through like this. So in this case, at least you just need one magnetic field. It's really hard to apply a magnetic field like this. So that's clever. It's a fairly big device. And maybe you guys have seen this work already too, but Mizumoto just published, and I'm sorry, I forgot to put the full reference here. This device, I don't know if you've seen this. It's interesting because TE comes in and it's split evenly. And then by this point, it's shifting to be TM in the bottom mode and TE in the top branch. And then by this point, you can see, I think it's this one. Oh, it's this one. It's all TM. Turns out this branch experiences the phase shift because it's TM, but the TE branch doesn't have phase shift. And so by the time it gets to the very end here, it's coupled back to TE. The TE from the bottom branch has shifted while it was TM. Now it's TE again, and they end up having an isolation from that. And actually, this device is only like 1 millimeter long, which is pretty good for these type of devices. But they found some problems with it because it didn't fully convert to TM in this bottom branch and a couple other things. But I thought this was a really clever idea. So there are different ideas. I just don't want to say like it's never going to work for TE, but you have to be a little creative. The ring resonator, the idea of the propagation constant going around this ring is different forward and backward if a section of the ring is magneto-optic. So if you have input going through this bus line, it doesn't couple with the ring, but when it's coming backward, because of that magneto-optic, it does couple with the ring. And then this is the data that they published. This is actually the first, there was a little SPIE that was published, and then this one on using that YIG as a seed layer. Actually, when Levy used to talk about this work, he would say, oh yeah, we did the Minnesota garnet, but only as a seed layer. Then we doped it and put down another layer. So that was fun. This is actually work that your group has done with Carolyn, where the sidewall was coated. And I think the moment then is applied up. Again, though, it's out of plane from the film. So this is a long waveguide. It would be nice if the moment were along the shape because it would hold better. But this does work for TE, and I brought your data in here just to make sure it's included. So these are the different devices. And honestly, when I talk to a lot of audiences, they're more materials people. They don't really know how they're used in these devices. Now, here's our new device that I think is really fun. And I guess I'd like to hear what maybe isn't going to work so well about it, because there's several things that I think are great about what we're calling non-reciprocal mode conversion. So instead of phase shift, we're just switching the mode. It's very much like Faraday rotation. We switch from TE to TM. And I will say, when I was brand new in this field, I had done just a little bit with waveguides, not much with optics, mostly materials. And I was taking a train in Tokyo, I think, with you, John. And I said, well, you don't get full Faraday rotation. And you said, well, it's not just that even doesn't rotate. It might start to rotate and it'll go back and start to rotate and go back because the propagation constant of the two modes is different. And that was, being a materials person working in optics, a little like, oh, that's why I can't get the Faraday rotation out of a YIG waveguide, because I don't match the propagation constants of the two modes. So I have to say, when I wrote this up, I thought, wow, like that must have been, well, I won't say how long. That was a long time ago that was the first time I'd heard about this. So I'm mode converting now in this waveguide. I have TE going in, it converts half TE to TM. I only need a half reciprocal mode conversion to end up putting the light forward as TE. Then it comes back TE, it half rotates back, and then it's TM by the time it comes out the other end. And the reason I have all these different lines is we were just saying, well, if I had a garnet core, how well would it rotate? And with the best garnets we can make at the moment, if you just did a garnet core, you would get that start to rotate, stop rotating, start to rotate. It would literally, if this is TE, it would just do this as it propagated down the waveguide. So we would quasi-phase match, which I'll show you next. Let me just show you that. Here's what the mode wants to do. Never quite getting to TM, maybe not even going more than like what we call 1 degree of Faraday rotation. But if you can stop the cladding from being magneto-optic, it will actually rotate and then not rotate. And when you get back to the place where the beat length is starting at 0 again, it'll rotate again at that point. And you can just build up your cladding to give you rotation by canceling rotation every half beat length. Turns out you can also, and this is just kind of the Stokes, I'm going to not go through this, but it's how it works on a Stokes sphere. But see over here, if you had negative and then positive, see where this light wants to turn back to TE, if you change the sign of your gyrotropy or your Faraday rotation, you'll swing back up instead of staying level even. Then swing up because it's negative, then positive, then negative, then positive, and so on. Turns out you can get a full mode conversion, or we only need a half mode conversion in a fairly short spacing. All right, so I guess what I like about the non-reciprocal mode conversion is we even have garnets that are good enough, these terbium iron garnets, that we could do this on a 500 nanometer core. And that means that a lot of lasers couple in one way or another to a thicker core, and then you taper, you can get reflections in the taper. So if you need your isolator to be 220 nanometer, you might have a lot of reflections already by that point. And so this was the schematic that Kartik made up to show maybe this is another way you're going to take your laser light coupled into a thicker core. But if your garnet could be here, then you're not worried about this taper reflecting a lot of light back. So on 550 nanometer, which actually, I'm sorry, it was this core right here, it also turns out that this beat length is pretty short, pretty long, because your waveguide is so isotropic that we ended up with a beat length of like 22 microns. So, you need a certain number of them, but it's not so much. 22 microns is very easy to make with photolithography. At least let me say it that way. So you don't need E-beam lithography. We did use it with David Hutchings and Glasgow to make this structure. And we're just trying different beat lengths to see what we got. The other thing I like about it is it's 1D. And the other thing that turns out, I think, is pretty interesting. We know some people at the Air Force, for example, that are interested in like fly-by-light kind of devices, even quantum devices. If you want to put light in, they don't want a magnetic field. Oops, right? They don't want a magnetic field near their other devices. But this is the shape anisotropy direction of these waveguides. So all of these measurements that we've made with David Hutchings are in remnants. We magnetized the sample and we measured it optically without a magnetic field. And we see decent Faraday rotation or a decent isolation. We'd like to get up to pi going forward and pi coming back to get an ideal isolator. But this is, right now we end up getting a 11 dB isolation, and we made a device, the best device length is 7 millimeters of silicon 500 nanometer core, which means the interaction with the cladding is not as much as 220, but we still were able to get an isolator with that 500 nanometer core. All right, so I know there's like 15 minutes, and I get the feeling that sometimes it's hard to listen to the same voice for an hour. And it's very rare that you go on a conference and the person that actually did the work in your lab is in the room with you. But because Karthik and Terry and I are kind of doing an I-Core tour, Karthik's here. So I asked if he would present this last bit and give you a change in tone.
Okay, hello everyone. My name is Karthik. I worked with Beth for the past 5 years at Minnesota doing a lot of the research on garnets, and some of it has already been presented. So I will talk a little bit about the last couple of slides. So one of the problems that you might have noticed already in the discussion so far is that garnets have to be annealed at a very high temperature, around 900 degrees Celsius, right after you sputter them, or even sometimes, pulse laser deposit them in order to actually crystallize and, benefit from the Faraday rotation that it has to offer. So something that we were thinking about was, why not, just like a lot of other materials that are, developed for a variety of transistor applications or even other optical applications, is there a way to transfer print garnets? And we started exploring that idea. And of course, I must admit here that this idea was not deliberate, it was by accident. But then we went back and we did a lot of analysis and study to find out what's actually causing exfoliation of garnet. So the basic premise here is that we are depositing garnet on patterned silicon wafer, which we call the handle wafer, and we're able to exfoliate it into a carrier platform and then print it on a device wafer. So now if you ask me the question, how do we actually achieve it? So the short answer is it's a controlled creep deformation. Now, if somebody here is in ceramic engineering, you might have learned that a lot of airline parts used in the 80s went through rigorous temperature testing to see where they would fail. And of course, you didn't want airlines, failing in the middle of their flight. And that's why they started studying creep deformation, which was basically a diffusion of vacancies at high temperature that would cause cracks in these materials. Now, what we do is we take this concept and we functionalize it to our particular scenario, and we deposit garnet on a silicon substrate, and by itself, it has a tensile strain at the interface. And by annealing it at a specific recipe, and which I have listed down here, we are able to facilitate a diffusion of vacancies away from the interface, such that it creates an exfoliation gap a couple of nanometers into the film, and that can be exfoliated quite conveniently by using a Scotch tape. So the first thing that I want to show you here is that the vacancy concentration that you see is exponentially related to the tensile strain at the interface. So as you can see, when we increase the tensile strain, which we basically do by increasing the thickness of the film, we are able to create a larger vacancy concentration for the different cations in the garnet and also for oxygen. And the baseline without strain is this red solid line at the bottom. Now, moving a step forward, one of the primary mechanisms that controls the diffusion of vacancy is called the Nabarro-Herring creep model. And we write down that equation, which is essentially a strain rate, which is a function of the grain size, or diffusivity constant at infinite temperature. And then you have the activation energy, the strain terms, and the temperature. Now we rewrite it to make it linear, and we add this pre-exponent factor, which will allow us to capture the different kind of diffusion processes that are happening in the material. And when we take our data and try to fit it with this linear form of Nabarro-Herring model that we have, we see that it fits quite well with a very high R-squared value, and we also get a diffusivity value from that fitting. So the first thing that we do is we compare this diffusion coefficient, and we see that it largely relates to the empirical diffusivities of iron and terbium, which tells us that iron and terbium is actually driving this process. And the other thing that I want to show you in the inset here is that when we compare the log-log plot of strain and stress, we are not very different from some of the bulk materials like polycrystalline yttrium aluminum garnet, a perovskite, and even a single crystalline yttrium aluminum garnet. But of course, for the polycrystalline films, you see that the slopes are comparable compared to the single crystalline. So moving a little forward, we take those films, we anneal it at the recipe that I just mentioned in the previous slide, and we see this beautiful stained glass pattern, which indicates that it's perfectly polycrystalline. And next, we take a cross-section TEM image of these films, where we see that we indeed have that exfoliation gap a couple of nanometers into the film from the interface. And when we do a line scan using EDS, we are able to see that perfect exfoliation gap. And on either sides of the exfoliation gap, you have the elements that we are looking for. And then you also have this interlayer, which forms as a consequence of some of the atoms diffusing towards the interface while the vacancies are diffusing away from it. And also the presence of iron and terbium at this interlayer confirms that indeed the vacancies that are created by those cations is driving the exfoliation process.
What is the gap?
Oh, that gap is, it's just air, it's nothing. Right, and of course, we did some optical microscope imaging where we see that we are able to exfoliate them into these beautiful large nanosheets, which are about 100 microns wide, and they're sufficiently large enough to transfer print them on waveguides or even pattern hall bars and electrodes to do some spin transport measurements. And looking at the magnetization characteristics through VSM measurements, we see that the saturation magnetization is quite comparable to its thin film counterpart on silicon, attached and intact. Although the coercivity reduces, but that's just a consequence of the exfoliated nanosheets losing their magnetoelastic anisotropy. And although the previous two slides said the manuscript is under preparation, I can very happily tell you that it's accepted and it's available online if you're interested in taking a deeper look at how we got to this point. And last but not the least, the most important thing that we're interested in is the Faraday rotation. And these films tend to maintain the Faraday rotation of about -26 to -2700 degrees per centimeter, similar to our thin film components on silicon. Now, this is just basically saying that we can pattern silicon and we can transfer these garnet nanosheets right at the place on the photonic chip that we are interested in, and we can entirely avoid the high temperature that is detrimental to lasers and the rest of the photonics. Right, so in summary, we saw a definition for Faraday rotation and how it's an important metric that defines a lot of the material, garnet material development. This is the off-diagonal component that's given here, which is essentially a function of the Faraday rotation. Some garnets also use something else called the Verde constant, which we haven't quite discussed, but that's another metric that we can refer to when we are looking at garnet materials. And we saw two kinds of devices that work either on the non-reciprocal phase shift, which are the interferometers and ring resonators, and the other kind being non-reciprocal mode conversion devices, which use quasi-phase match cladding to overcome modal bi-refringence. And lastly, we saw a couple of different ways of integrating garnet. It can be hybrid, heterogeneous, transfer printed, and the garnet can be grown either using LPE, pulse laser deposition, or sputtering. And lastly, we realized that isolators need TE mode to operate, and that will be convenient as the lasers are also TE mode. And thicker core silicon waveguides are preferred because that will allow us to integrate it before the light sees any tapers or couplers before moving further into the photonic chip. So I think with that, we would like to acknowledge every single collaborator and funding agency that has been instrumental in all our research. And I think it's time for questions. Thank you so much.